So last time we talked about the second law. The second law says, for any spontaneous change, the entropy of the universe must increase. And we saw this formula, delta S universe must be positive for a spontaneous reaction. The universe is comprised of the entropy of the surroundings and the change in entropy of the system. But it's kind of tough to keep track of universe and surroundings and systems when they all have the same variable name, right? It's S of the universe, S of the system, S of the surroundings. Yeah, it's a little bit hard. But what we said was we can change this delta S surroundings to be related to delta H of the system, delta H of the reaction. We said whatever entropy is entering the surroundings has to be exiting enthalpy from the reaction. We made that substitution previously. This delta S system, if we carry that on down, we said this combination needs to be positive in order to be a spontaneous reaction. I don't know why I decided, oh yeah, okay. The only thing I did here was change system to reaction. Yeah. So based on our equation here that now has two sets of reaction conditions, we can say two things make a reaction occur because delta S universe must be positive for a reaction to occur. Either the reaction is exothermic and it dumps enthalpy into the surroundings, which causes delta S universe to increase. Being exothermic does not mandate that the reaction is spontaneous, but it's fairly likely. If it's exothermic and positive, it's always spontaneous. If it's exothermic and negative, as long as this term is larger than that term, it's spontaneous. Bear with me, hold on. The other possibility is delta S reaction. You create greater entropy in the products than the reactants. So if this term is positive, it's likely to be spontaneous. If this is positive and positive, this term has to be larger than that one in order to be spontaneous. You'll catch it, I think, in a moment. When will it never be spontaneous? When delta H is positive and delta S is negative, which means when they're the opposite signs of the description here, right? Right. So it's convenient to have the delta S universe, the second law equation, written in terms of a reaction, but let's make it even a little more clear so that we don't have to keep up with S universe and S reaction, because it's really confusing to have the same named variable in the equation but for different parts, as in universe and reaction. So if we multiply both sides by negative t, that means delta S universe times negative t equals negative delta H reaction over t. That simplifies to delta H of the reaction minus T delta S, right? Multiply this by negative T. So there's this dude that came in, just by Gibbs is his name. There's this dude that came in that says, let's define a new state function. Let's get rid of this delta S universe term because it's confusing to try to keep up with reaction and universe stuff. And let's define this new term delta G as S times S universe times negative T. That is now known as delta G. So delta S universe times negative T is delta G. If you bring down the rest of the equation, delta G of the reaction, I should write that, is equal to delta H of the reaction minus T delta S of the reaction. Reaction, reaction, reaction. We don't have to keep up with system and surroundings and universe. It's just reaction, reaction, reaction. That's excellent. So delta G is equal to negative T times delta S universe. Why did I say that backwards? I don't know. What's the criteria for spontaneity? Delta S universe must be positive to be spontaneous. So a positive times a negative temperature, it means the criteria for delta G is that delta G must be negative. Because negative times a negative would be a positive. Yeah. It's just two ways of writing the same thing here and here. Delta S universe must be positive to be spontaneous, which means delta G must be negative to be spontaneous. Okay, so this is kind of a big deal, this new state function G, delta G, Gibbs free energy. This is a this one is a super useful equation, and we will use it pretty frequently. A few things about our state function G. Negative, spontaneous. Positive, non-spontaneous. We might say it's spontaneous in the reverse direction. I don't love saying it that way, so I probably avoid saying it that way most of the time. Negative is spontaneous, positive is non-spontaneous. 0 is said to be at equilibrium. So we saw this a little bit before, but at equilibrium, delta G equals 0, so you could plug in a 0 here and solve for temperature. For phase changes, like solid going to liquid, liquid going to gas, gas going to liquid, for phase changes, those are equilibrium processes, and delta G is equal to 0 for a phase change. So sometimes you will be asked to find the temperature of a certain phase change. Delta G is 0 for phase changes because those are equilibrium processes. Yeah, all these are constant temperature process. That matters. All right. There's a couple of ways that we can use G, and one way is this. Given a delta H, given a delta S, solve for delta G, right? Delta G, standard, that's that little 0, that little naught up there means. Negative 1036.2 kJ minus 492 Kelvin times negative 152 joules per Kelvin. And hopefully you say, something's wrong there. And I say, you're right, something's wrong there. One of the biggest issues is unit disagreement when you're trying to do these types of problems. I don't care if you change both of them to kilojoules or change both of them to joules, but they have to be in the same unit to be able to be added together. What I'm going to do is mark out that decimal and move it 3 times to make 152, negative 0.152 kilojoules per Kelvin. Because my delta H is a really large joule number. If I do that multiplication, addition, subtraction thing, negative 961.22 kilojoules. Because my Kelvin canceled out, right? Right. One thing that I want to say is that delta G changes dramatically with temperature. Delta H and delta S are relatively temperature stable, like relatively temperature independent. If you look in the back of our textbooks, it has tables for delta H and delta S at 25 Celsius, but that's far from 492 Kelvin, but those values are still pretty close. The delta H and delta S are still pretty close, 298 to 492, because delta H and delta S are relatively temperature independent. But delta G is very dependent on temperature. See, temperature is in the equation. Delta G is very dependent on temperature. Okay. So if we do a little more color coding, because I think it's more clear on this delta G formula, delta G for delta H, exothermic reactions are typically spontaneous, so I will make that green. Endothermic reactions can happen, but they're not as likely. Delta S reactions are typically positive, means spontaneous. So I'm going to say, again, we're working in Kelvin temperatures here. So this is always a positive value. Temperature always is. So this term is given the same sign that delta S has. So this is a positive. This term is a positive if delta S is a positive. So we can have a positive, which indicates spontaneity in general, or we could have a negative, which is less likely to occur, but still could occur. This bottom situation says endothermic reactions that have a negative delta S sign will never, ever, ever occur. Delta G has to be what sign to be spontaneous? Negative. A negative delta G indicates spontaneity. This bottom will never have a negative delta G. The top one will always have a negative delta G. And then the two in the middle are temperature dependent. If this term is large enough, it will drive this reaction to give you a negative delta G. If this reaction, if this term is large enough, it will drive this reaction to be spontaneous. The green thing is said to drive the reaction forward. This one is enthalpy driven. This one is entropy driven. Hard to write the right thing. Enthalpy driven, entropy driven. If we look at a little table from our textbook, positive, positive, we said reaction proceeds spontaneously at high temperatures. So that means if this term is big enough, if temperature is high enough, if this is big enough, it's an entropy-driven reaction. And then the other one was a negative, negative. If we look at that one, negative, negative. The reaction is spontaneous at low temperatures because this term has to be small enough that this one can overtake it, right? So high temperatures makes it spontaneous. Low temperatures makes it spontaneous. Look, look, look. Always positive. That's our bottom situation. Always negative. That's our top situation. Yeah? There's a table in the textbook that you could memorize. But who wants to memorize when you don't have to, right? Right. Okay. Goodbye.